So we're going to do glycolysis today. This is how you break down glucose to pyruvate in the cytosol. And hopefully we'll also talk about how your body converts pyruvate into acetyl-CoA. And that'll unify the two pathways we've been talking about, triglyceride metabolism and carbohydrate metabolism. So first step we talked about last time, which is that glucose gets modified on the C6-hydroxyl with a kinase called hexokinase using ATP to convert the alcohol to a phosphoester. And I mentioned this commits a glucose molecule to glycolysis because this step is irreversible. You can tell, even if you don't know the delta G, that it ought to be irreversible because you're replacing a weaker phosphoanhydride bond, a more reactive phosphoanhydride bond in ATP with a more stable phosphoester bond in the product. Product is called glucose 6-phosphate. And we won't show the mechanism of this because you've seen a kinase mechanism before, so I'll just refer you to that. So the second step involves conversion of glucose 6-phosphate to an isomer. Glucose, what kind of carbohydrate is it? Is it an aldehyde or a ketone? That was not rhetorical. Somebody say, is it an aldehyde or a ketone? Well, right now it's neither. It's a hemiacetal. But if it opened up, what would it be? Aldehyde, right? You can tell that because the anomeric carbon is bonded to a carbon and a hydrogen. We're going to isomerize glucose to fructose 6-phosphate, and you'll see that fructose differs from glucose in that fructose is a ketose. We're going to draw it in its cyclic hemiacetal form. This hemiacetal carbon is carbon 2. So here is carbon 1 of fructose. And we're no longer really attempting to draw anything like a chair because conformational properties of 5-membered rings are more complicated than those of 6-membered rings. So just to be really clear about what's happened here, 1, 2, 3, 4, 5, and 6 for glucose, 1, 2, 3, 4, 5, and 6 for fructose. Do you see how the hemiacetal carbon used to be on carbon 1, now it's on carbon 2? So that's an isomerization reaction. And conveniently, the enzyme is named glucose 6-phosphate isomerase. And it turns out, if you were going to think about how to convert an aldehyde to a ketone, you've had to move the hemiacetal carbon over. You might think, we need to reduce carbon 1 to an alcohol and then oxidize carbon 2 to a ketone. But it turns out that's not necessary, and you can accomplish this transformation from glucose to fructose 6-phosphate simply by proton transfer or tautomerization. So to see how this is, I'm not going to show you, see how this works, I'm not going to show you the ring opening mechanism. You've seen that before enough times that I feel like you ought to be able to get it. Let's just draw, though, the ring opened product, where carbon 1 is now an aldehyde. By the way, as we do this, pay attention to the fact that C3, C4, and C5 are unchanged in glucose versus fructose, and they have the same stereochemistry. So that's the ring open form of glucose. We'll now draw the ring open form of fructose, only we're moving backwards, which is why I've called it ring closing. got to imagine this bond between carbon 5 and the C5 hydroxyl group is behind that bond between carbon 3 and the OH group in the front. Carbon 2 should be a ketone, and then you've got carbon 1 here. Okay, so it turns out you can get from here to here through a couple of tautomerization steps. All right, so we'll do what we will tend to do with biological proton transfer reactions. That is, we'll condense a few of them in the same step. So we're going to use a base from the enzyme active site to remove the C2 hydrogen. Notice that C2 hydrogen, sorry, struggling with the drawing, is alpha. It's on a carbon that's alpha to a carbonyl. Therefore, it makes sense that a base in the enzyme active site should be able to deprotonate that alpha carbon. Okay? Now, when you deprotonate an alpha carbon, you get an enolate, right? And that enolate is negatively charged on the alpha carbon, and where else? Carbonyl oxygen by resonance, right? And so it's not too much of a stretch to imagine that these electrons kick down to form a pi bond, and in the same step, the carbonyl oxygen gets protonated by some acidic group in the enzyme active site. And this is going to take us from the aldehyde form to an enol form. So typically we've drawn tautomerization from a carbonyl form to an enol form. We've typically drawn that before more slowly. We've drawn the enolate first, and then in the second step we protonate on the carbonyl oxygen. Instead, in an enzyme catalyzed mechanism, we're showing that all at once. So this is the deprotonation of the alpha carbon. This is reprotonation on the carbonyl oxygen. Hopefully you're okay condensing those two in one step. If you want to draw them out separately, that's fine too. All right, so let's finish drawing this intermediate. This is carbon 1, 2, and 3, and then we'll draw the rest of the molecule, in the same way. And then I'm missing a up OH group on carbon 3. I'm showing the proton there so that we don't lose track of stereochemistry, but there we go. This intermediate is an important one. This is called an ene diol. From the perspective of the aldehyde carbonyl, this is the enol, oops, that's an eraser. This is the enol of that aldehyde, but it's also the enol of this ketone. Do you see how the ene diol is the tautomer of both? Yeah.
Is it important that the OHs end up cis to each other?
No, it's not important that the OHs end up cis to each other. And I'm not sure whether one is preferred over the other, but the ene diol is an intermediate that doesn't last very long, so its stereochemistry isn't important. All right, so the ene diol, the nice thing about this ene diol intermediate, is that it is a tautomer of both the aldehyde and the ketone. So it turns out that we can generate the ketone by another series of proton transfer steps that are just going to be the mirror, really, of what we did earlier to the open chain form of glucose. That is some kind of base in the enzyme active site, possibly the conjugate base of the acid that protonated the ene diol. is going to, sorry, I got the wrong proton. Some base in the enzyme active site is going to remove the proton from the C2 hydroxyl group. That would generate, if we just push the arrow there, that would generate an enolate. And that negative charge on that enolate would be on both the carbonyl oxygen and this alpha carbon, the one that's alpha to carbon 2. But if we want to condense that and all have it be in a single step, we can have electrons kick down here, and then we can protonate on C1, which is the alpha carbon relative to C2. The new proton that just got added in this tautomerization step is on C1, and the new pi bond that just got made is here between C2 and the oxygen. So 2 tautomerization steps, and the only thing new we're doing here that we haven't done before in tautomerization is we're condensing the deprotonation and then reprotonation on either the oxygen or the alpha carbon, all in the same enzyme catalyzed step. Okay, so via an enediol intermediate, 2 tautomerization steps basically moves the carbon-oxygen double bond over 1 carbon. That allows you to isomerize from glucose to fructose. And there's a reason we want the carbonyl to be there, but that reason's not going to become apparent for another step or so. Questions so far about that? All right, let's keep going. Step 3, we'll take fructose 6-phosphate and we're going to put another phosphate group, this time on the C1 hydroxyl. Oops. And again, you're going to be thinking, well, shoot, why are we consuming another molecule of ATP? And I'll tell you, don't worry about that at this point, because as we do the math, you will see we're going to recover both molecules of ATP that we invest, and we're going to get 2 additional molecules after. So nature will double its talents, as it were. Too soon. You got general conference hangover? Is that what's going on? You don't want to hear any scripture references? Well, too bad. You just don't want to hear about the 10 virgins? Okay. Phosphofructokinase. All right, so here we go. ATP, again, phosphoanhydride bond on ATP is going to convert the C1 hydroxyl into a phosphoester. So you'll see that fructose 6-phosphate is going to have 2 phosphate groups on it. Fructose 1,6 bisphosphate is going to have 2 phosphate groups on it, one on C1 and the other on C6. And this is going to introduce a certain kind of symmetry into the molecule. We're going to eventually break fructose 1,6 bisphosphate up into 2 equal parts, and C1 and C6 are going to become identical. And from that point on, nature can use the same machinery to process both halves of fructose 6-phosphate. I told you nature was efficient. And the goal, we're going to eventually convert fructose 1,6 bisphosphate into 2 equal 3-carbon units, which nature can treat in the exact same way. This is a kinase step. It's named for the substrate, fructose 6-phosphate, phosphofructokinase. It's kind of fun to say. And the bis here is a word that, why not just say diphosphate? I think they're trying to indicate that it's not 2 phosphate groups connected to each other, but 2 phosphoesters on separate parts of the molecule. Okay, questions about that kinase step? It's also irreversible, also very downhill because you're replacing a phosphoanhydride in ATP with a phosphoester. All right, so this is the cool part. I mean, it's been all cool so far. I know you've been thinking, wow, this is cool. This is a part we've been training you to recognize since almost the very beginning of this class. There's an enzyme called aldolase that's going to break the glucose molecule into two separate pieces. The first is an aldehyde, and this is going to correspond to carbons 4, 5, and 6 of fructose 1,6-bisphosphate. This molecule is called glyceraldehyde. And then the other 3 carbons, corresponding to carbons 1, 2, and 3 of fructose 1,6-bisphosphate are going to be here. This is a molecule you've seen before, dihydroxyacetone phosphate. And this is the molecule that we made previously from glycerol, from fatty acid, or rather from triglyceride metabolism. Okay, so the fact that the enzyme is named aldolase suggests that it's catalyzing an aldol reaction. An aldol reaction is a reaction between an enolate, alpha carbon, and the carbonyl carbon of another molecule. And the product of an aldol reaction is a beta hydroxycarbonyl compound. Now, it turns out this enzyme is named for the reverse reaction, combining dihydroxyacetone phosphate with glyceraldehyde to get fructose. But in the forward direction for glycolysis, this direction to the right is called a retroaldol reaction. So, let's look at fructose 1,6-bisphosphate, and let's see, based on the structure, whether we can tell where the disconnection should be. So we're going to, again, not show you the mechanism for ring opening because you've done that before for a hemiacetal, and I think you'll be able to get it. Let's just draw the ring-opened ketone form of fructose 1,6-bisphosphate. The ketone is here on C2, and then C1 has the phosphoester on it. So 1, 2, 3, 4, 5, 6. Now, C2 is the carbonyl carbon, C3 is the alpha carbon, C4 is the beta carbon. Hopefully you can see there and identify the beta hydroxycarbonyl compound that is indicative of an aldol product. It's right there. Now, tell me why nature, now with that in mind and knowing what the molecule is going to split up into, tell me why it's better to do this than to do a retroaldol reaction on the aldehyde. Let's just think about carbon, alpha carbon, and beta carbon. In a retroaldol reaction, which carbon-carbon bond in this molecule would be the one that would be broken in a retroaldol reaction? Another way of asking that is, which bond is made in an aldol reaction? It's always the bond between the alpha carbon and the beta carbon. The beta carbon is the one where the alcohol is, okay? So if we did a retroaldol reaction on glucose, that would give me how many carbons in the enolate portion? 2, just 1 and 2, and then the aldehyde portion would have 4 carbons. And nature could have chosen to do that, have a 2-carbon chunk and a 4-carbon chunk, but then you've got to have different machinery to deal with the 2 different products, right? which is probably inefficient. But by sliding the double bond over just one space, you now generate an intermediate where if we break this bond between C2, C3, and C4, we have 2 3-carbon pieces. You see carbons 1, 2, and 3, and then 4, 5, and 6. And not only that, but look at the products. What is the relationship between dihydroxyacetone phosphate and glyceraldehyde? Is it similar to the relationship between fructose and glucose? Glucose had an aldehyde on C1, fructose had a ketone on C2, and we were able to interconvert them via an enediol intermediate. Similarly, glyceraldehyde has an aldehyde on C1 or C4, whatever you want to call it, and dihydroxyacetone phosphate has a ketone on C2. We can also interconvert these via an enediol intermediate. So nature's a genius here because we can clip the molecule into 2 parts that are easily interchangeable, and from that point on, we don't have to duplicate machinery anymore. We can use the exact same enzymes to process both parts of this molecule. So that's kind of cool, right? And as I said before, if you have eyes to see, you can sort of see the hand of God in this, and the chemistry just makes sense. So how are we going to show the retroaldol reaction? Turns out it's quite easy to do. We can do it in one step of arrows. Normally, if we were drawing a retroaldol reaction, we would deprotonate the beta hydroxy group to generate, and electrons would kick down to generate an aldehyde. Then these electrons in the bond between 3 and 4 would move over here to form a resonance stabilized enolate, which we would later protonate on the alpha carbon. Because this is an enzyme catalyzed mechanism, we can show those steps all happening at once. So we'll have a base from the enzyme active site do the deprotonation of the beta hydroxy group. Electrons will kick down to form the aldehyde. We would normally show this bond between C3 and C4 breaking to go onto the alpha carbon as an enolate. And then in a second step, we would protonate that enolate. But because we're in an enzyme active site and because we're sort of trying to save time, we'll show that enolate getting protonated on the alpha carbon by some group in the enzyme active site, all in the same step, and that leads you to those 2 products. You are welcome to go through and show that out, show those steps out stepwise if that makes more sense to you, but it's important that you recognize this as a retroaldol type reaction. All right, questions about that? Okay, so step 5 is going to be the conversion of dihydroxyacetone phosphate to glyceraldehyde phosphate. So we already have one equivalent of glyceraldehyde phosphate, but now we're going to convert it into, but now we're going to get 2 by converting dihydroxyacetone phosphate into glyceraldehyde. At this point, I'm going to drop the 1, 2, 3, 4, 5, and 6 that we used previously for glucose, and we'll just start numbering things. Oh, yeah, sorry, clicked the wrong thing. We'll just start numbering things in a simpler way, starting with C1 on the aldehyde and glyceraldehyde and so on. Okay, so this step is catalyzed. Oh, and I guess on the retroaldol step, this is totally reversible. The delta G for this reaction is really small. You don't need to memorize the delta G for reactions. It's irreversible, but it's basically 0, meaning nature can go backwards and forwards through this reaction step. Okay, the enzyme that catalyzes the interconversion of dihydroxyacetone phosphate and glyceraldehyde phosphate is one of the most efficient enzymes of nature. People call it a perfect enzyme because it's fast enough that if it couldn't really be any faster, or if it were, diffusion in water would be slower than the enzyme. And so it's one of the most efficient enzymes ever. It's called triose phosphate isomerase, or some people call it TIM. This step is, again, reversible. And it's going to happen via an enediol intermediate. So in the same way that we showed before for the interconversion of fructose and glucose, we'll remove this alpha proton and we'll protonate the enolate in the same step. If you want to show that stepwise, if you actually want to show an enolate intermediate, that's fine with me. That's going to generate an enediol. I'm sorry. That's terrible chemistry right there. So erase, erase, erase. Painful, isn't it? All right, give you a minute to reset. The problem was I needed to go with the other alpha proton. Some of you were like, that looked terrible anyway, so. Base removes the proton, we make an enolate, and we protonate the enolate all in the same step. And that will generate this enediol intermediate. Again, the stereochemistry of those two alcohols relative to each other doesn't matter. What does matter is once you get to that enediol intermediate, that you can, through another tautomerization step, get to glyceraldehyde. And that's going to involve a basic group on the in the enzyme active site, removing this proton, electrons kick down to form an aldehyde, and then we're going to protonate on the alpha carbon, that is C2. And notice that we're setting the stereochemistry at C2 in this step. The enzyme is going to protonate that enediol from a preferred face to give you the correct stereochemistry at C2. All right. Sorry about that mistake earlier. Any questions you want to ask about the isomerization versus the enediol? Go ahead.
So these are just two different mechanisms to get the glyceraldehyde? Two options, or is that the mechanism of TIM?
What I've shown you here is the mechanism of TIM. Yep.
And so is TIM like enzyme B?
Both of these groups are in TIM. Yep, the TIM active site has basic groups and acidic groups. Yep. So note that one of our molecules of glyceraldehyde comes from the aldolase step, and then the second molecule of glyceraldehyde comes from the TIM step. At that point, we've converted glucose into two equal 2-carbon units. So this is important. What we're going to do for the remaining steps, I'm just going to show once on one molecule of glyceraldehyde, but you have to remember that whatever we do happens twice to keep everything balanced. All right? Okay. I want to make sure I get this right. Sorry, I'm not having a brain issue at the moment. I'm just seeing something in my notes that I learned is maybe not accurate, so I want to make sure I get it right. Do you ever wonder if your professor stands at the front of the class and Googles whether or not you're actually getting anything that you paid for in your education? At least I'm honest about it. Okay, yep. Very good. All right. So the next step is going to be oxidation of, and this is a somewhat complicated mechanism. It's going to be oxidation and some shenanigans at C1, sort of nucleophilic acyl substitution at C1. So we're going to take glyceraldehyde 3-phosphate and, oops, yep. And we're going to oxidize it and convert C1 to a phosphoanhydride. And this is called 1,3-bis phosphoglycerate. Now you can see that this is an oxidation reaction because we start out with an aldehyde and we end up with something that's at the carboxylic acid oxidation state, right? It's now got 3 carbon-oxygen bonds with that C1, an oxidation reaction. Nevertheless, you're going to see that this reaction is reversible, which is fascinating, but makes sense because we're converting a C1, we're converting a reactivity level 1 group, an aldehyde, to an acyl phosphate, also reactivity level 1. So even though we're oxidizing and getting something here, we're starting with an aldehyde, and so it's just transferring one reactive functional group into another, and so it's not a massive change in energy. This reaction is going to involve NAD+, and you're going to get NADH out. There's going to be a proton lost. And we're also going to need, I'm not sure how best to do this, we're also going to need a molecule of phosphate. Inorganic phosphate is what the biochemists call it. This molecule of inorganic phosphate is going to end up as this phosphate group on the carbonyl carbon. Okay, so let's talk about the mechanism. It turns out that the nucleophile in this reaction is a cysteine side chain in the enzyme active site. And this is what I was Googling to make sure I got right. A base removes the proton on the cysteine. The cysteine attacks the carbonyl carbon. Normally we would just draw a tetrahedral intermediate, and that's fine, with a negative charge on the oxygen, but sometimes there's evidence that the enzyme actually protonates that tetrahedral intermediate as it's forming. So we're simply going to show that. That's, and the product that we're going to get, and I'm going to need a new page to do that, is going to look like this. It's an enzyme-bound intermediate. This is C1, C2, C3. This is a cysteine in the enzyme active site. And this intermediate is called a hemithioacetal. It would look like a hemiacetal if that were an OR group, an alcohol, but it's a cysteine, it's a sulfur, so it's a thioacetal. This hemithioacetal is the one that's gonna get oxidized by NAD+. So we could skip over this because you've seen it before, but repetition is not a bad thing. This is NAD+, and a base from the enzyme active site is going to remove the proton from the alcohol. Electrons will kick down to form a carbon-oxygen pi bond, and the hydride is going to get delivered to NAD+ via the usual mechanism. So this is the proton that gets removed, and this is the hydride that gets delivered. Oops. And then the product of that will be a thioester and NADH, which I'm just going to abbreviate as that. So that was the oxidation step. Do you see how we moved up from an aldehyde, or from starting with an aldehyde? Now we've got, oh man, there's an eraser. There we go. Now we've got a thioester. At this point, going from the thioester to the bisphosphoglycerate is simply nucleophilic acyl substitution. So I'm going to, well, that's crazy, isn't it? I'm going to just write nucleophilic acyl substitution here. And I'm going to leave that to you to draw, though I will give you the first step. Here is the inorganic phosphate ion. You're going to have the oxygen, one of the oxygens. Ooh, that's ugly. Probably we should put a proton on one of those. That's the form at which phosphate would exist at pH 7. It's going to attack the carbonyl carbon. You're going to get a tetrahedral intermediate. You can draw that intermediate. You can then show electrons kicking back down and the sulfur, the cysteine thiol leaving. Okay? I think you can connect those dots without too much trouble. That gets you to bisphosphoglycerate. All right. So step 7, and remember that everything that happens from here on, from step 6 onward, happens 2 times. So we've just generated 2 molecules of 1,3-bisphosphoglycerate. In step 6, oh, that was step 6, sorry. In step 7, we're going to recover our investment of ATP. So here's 1,3-bisphosphoglycerate. And this is the beauty of glycolysis. This step is totally reversible. We're going to generate ATP, and it's totally fine. And the reason why is we're going to be converting an acyl phosphate into a phosphoanhydride. That's 2 level 1 reactivity carbonyl type molecules. And it's totally fine and irreversible, not even a huge free energy change, because we're just replacing one acyl phosphate with a phosphoanhydride. So in this step, you're going to use ADP as a nucleophile, and you're going to get ATP out. And the product is going to be 3-phosphoglycerate and ATP. So converting an acyl phosphate into a phosphoanhydride. And remember, because this happens twice, we've just paid off our investment. So how does this mechanism work? This phosphorus here is going to become the gamma phosphate group of ATP. I will draw just the phosphate portion, of ADP. Oh shoot, now I'm in it, so we just as well continue. There's the ribose ring, there's the adenine base. Lone pairs on the phosphorus are going to attack, lone pairs on the oxygen rather, are going to attack the phosphorus you're going to get a pentavalent intermediate, and then electrons are going to kick down and kick off this phosphoglycerate as a leaving group. I guess I'll show that intermediate. I wasn't gonna, but let's go ahead and show it. So this is now and I'm going to abbreviate the ADP portion. Hopefully that's okay. This is going to become the gamma phosphate of ADP. Electrons on one of the oxygens of the phosphoryl group is going to kick down and kick off the carboxylic acid as a leaving group. This type of reaction is called substrate level phosphorylation. That means you're getting ATP from the substrate, as opposed to having to go through the ATP synthase in mitochondria. All right, so we paid off our debt, but notice our molecule 3-phosphoglycerate still has a phosphate group on it. Now where it currently is, it's a phosphoester, and phosphoesters are at level 2 reactivity. But we want to make ATP. And in order to do that, we're going to need to convert that phosphoester into something that's a little bit higher in reactivity. So let's show you how that happens. And those will be steps 8 and 9 of glycolysis. Before we do that, any questions? All right. So step 8 takes 3-phosphoglycerate, where the phosphoester is on the C3 hydroxyl group, and it's going to move the phosphate over to the C2 hydroxyl group. And the mechanism for this reaction is known, but I'm not going to ask you about it. Again, everything other than steps 1 and 3 so far have been reversible. But you go from 3-phosphoglycerate to 2-phosphoglycerate. It's not that complicated if you want to look up the step. It's just kind of weird because it involves a histidine side chain that's been pre-phosphorylated. And that seems kind of strange. You've never seen that before. But basically what happens is the phosphorylated histidine transfers a phosphate to the 2-phospho group. And then it steals the phosphate from the 3-phospho group. Not that hard, but I decided it wasn't worth the trouble. So if you want to see it, come talk to me. We'll discuss it in more detail. But I promise not to ask you about the mechanism for this step. Enzyme is called mutase, mute for movement or change. It's changing where the phosphate group is. Oh, I didn't tell you what the enzyme was for step 7. Guess. What do you think the enzyme name is? Oh, I also didn't tell you what step 6 was either. Did I? Okay, I don't want you to guess on step 7, but I do want you to guess on 6. What do you think that enzyme is called? It involves an oxidation step. Oxidase makes sense, but what are you removing? You're removing a proton and a hydride, so that's a dehydrogenase. Yeah. So this enzyme is called glyceraldehyde 3-phosphate dehydrogenase, or abbreviated as GAPDH. That's a pretty common enzyme that you'll see if you ever do some stuff in biochemistry. It's pretty evenly expressed in different cell types, is often used to as a control for whether you loaded the right amount of protein in your Western blots. None of that may sound like you know it, like it does make sense, and it won't. If you ever work in a biochem lab, you may have to deal with it. Okay, and then step 7, what do you think this one is called? I do want you to guess on step 7. What do you think this one is called? Kinase. Why would you say kinase? Oh, go ahead. No? I don't know. It looked like you had something to say, but that's okay.
It looks like it's removing a kinase, like removing a phosphate group. So it's like just either way.
Right. So if it were starting, that's interesting. We would call it a kinase if you were starting here, and then ATP would be transferring the gamma phosphate, and then you get this product. And that's actually how it's named, even though it's backwards. We don't call this reaction an ATP synthase. It's actually named phosphoglycerate. Oh, I run out of space. That's embarrassing. Kinase. It's named for the reverse reaction. And that's irritating, but again, biochemists have to pick one way instead of both, and so they just pick the one that is easiest and makes the most sense. So yeah, this is a kinase, even though we're running it backwards to get 3-phosphoglycerate. Okay, step 8 is mutase. You still hanging in there? No? You're like, done. I'm out. We have 2 minutes, but you're begging me to stop.
Are we almost close to being done?
With glycolysis, we got 2 more steps, 9 and 10. Boo. Okay, fine, get out of here. We'll do it next time.